Hi, I'm Chris from Airwindows, and today I'm going to take you on a little reverb journey before giving you a new toy that you may or may not be able to effectively use. But this is what I've been working on in recent weeks, and so this is what I'm putting out this week. It's not a plugin itself. Let me show you some plugins. Here. This file says verbhistory.flac. So I make my plugins out of what's called householder matrices. And those can sound something like this. That's a householder matrix that is kind of rigging out very far. And I've used that to make things like, for instance, here is Verbity. So you've got this plugin. This is an old one that I made, Verbity. And then I've also made things like Chamber. It's a slightly different flavor there because the delays are arranged differently. And the same mechanic of 4x4 matrix gives you Galactic. This is the famous Galactic. And all of those have been 4x4 matrices. That's what I started out doing. But I wanted to go farther than that. So the next thing that I did was start to invent the 5x5 matrix, which doesn't work in quite the same way as the 4x4. Some of the factors by how you do it, you use slightly different formulas for things. But what it does is it gives you a sound that's a little bit more like this. Compare that to Galactic. It's kind of brighter, but it's less complicated. That's more complicated. This is one of my 5x5 matrices. There's a goodly number of these. It started with, I think Cathedral was the first one that I did. I've got 3 different versions of Cathedral, each of them trying to do it better. I've got Guitar Hall, and I continue to work on this stuff, which brings me to what I'm not able to give you this week, but probably very soon. What if 6x6 matrix? So 5x5 matrix sounds like this, right? What if this? Now the question arises, yes, that is further in the direction that I was doing, further in the direction of complexity. And I can show that quite easily by bouncing between Verbity, Plate 140, and the 6x6. Here's Verbity. Here's 140. Here's the 6x6. So the deal there is those aren't all exactly the same settings. I got them as close as I could, but the way that I generate those sounds, or indeed sounds like this, which is bad, are to try to work with an application I developed, and that's what's giving me these actual matrices. Say hi to the thing that I'm actually giving out. This is called IntoTheMatrix. You'll notice that we have a screen of text over on the side that you can scroll with the scroll bar or whatever, and it says how to use this crazy thing. You still might not be able to use this crazy thing. Not only that, it doesn't make a noise all by itself. What it does is you pick a room size, which I have worked out to try to be roughly around what you'd get by telling it this many seats. And you set a few controls. Here I've got it and it says G, bloom, space, sustain, R, naturalness and spacing, and B, darkness and depth. And there's letters to either side of these things. What that does is if you type in a different letter, it will set it to that. And then we have these buttons down at the bottom, and those are the size of the matrices. So if you have a 200 seat thing and you used, say, a 3x3 matrix. So what's a householder matrix, and what would a 3x3 matrix be? It would be 9 different little delays. And in order to get from beginning to the end of the output, you'd go through a sort of box of these delays. The sound that you do goes first into the first 3, and each of those goes into the following 3, and then each of those goes into the following 3. So you have 9 delays, but you get a bunch more combinations, because any sound is going to have to go through this little array of things with at least one path from, say, left to right. Technically, what I'm doing also is I'm running left to right and top to bottom, and that's kind of how I use the householder matrix. But that's getting more fancy. It exists in a bunch of my stuff, but you don't have to care about that right now. What would you see? You'd see something kind of like this. And what we see here is the delays plotted over time. We've got this little blur of like red spots there. Naturalness in spacing means that is depicting the spaces between each of these dots, and each of these dots are how long the total delay would be when you went through first the first 3, and then the next, and then the next, in every possible combination. You get this many dots, not just 9, because the end result is not really going through 9 delays, either all in parallel or all in series, but combinations of those things. And what it's doing, grinding away doing these various things, we've got it updating very quickly, is it's trying to get to a high score. It's trying to find the best possible combination of those according to these 3 parameters. With the 3x3, it doesn't do much with the parameters. But as you can see, it's kind of animating, it's updating. So I can quit out of there and run it again, because it's not really designed to do multiple. You're supposed to run it, and then it'll run perhaps overnight and find the best possible outcome. What if we hit 4x4? It's going to look different. We hit 4x4, and now we see a more dense cluster of dots and different things showing up. And we see this area on the bottom. There's sort of extra green dots around here. There's a meter here showing what this is doing. And it's still kind of spaced out. There's still a bunch of specks with a bunch of space in between the specks. And they're in some different colors, like there's cyan and green ones. And the red area has gotten more complicated. That's naturalness and spacing. It is measuring what space between each of these spots, and it's going like a typewriter. It's left to right in successive lines, and it's showing the overall picture of the reverb impulse. Sort of both left and right on top of each other. This is how I've been generating these things since like post-galactic. And we're looking at a 4x4 matrix. Now that produces, as you can see, a goodly number of spots, and yet maybe we can go one further. After all, everything since kCathedral has been doing 5x5 matrices. Would you like to see what that looks like? We're going to start getting a little more interesting. Notice also what's being drawn in the text box over there, because I'm going to tell you what you can do with that if you can compile my open source plugins. And I probably can't help you do that, but if you can make it work, then you can use this. Here's a 5x5 matrix. Remember, it's the same thing, 200 seats, and these controls are set the same way. And we're going to start seeing something a little bit different now, because now we see kind of a cloud. The way a householder matrix works, if you start doing increasingly larger spaces, we've gone from like what, 16 delays in 4x4 to 25 delays in 5x5. But look how many more outputs we have. We've got a whole little cloud going on with a lot happening, and that's before we start regenerating. That's before we start feeding back the output into the input. And now we're seeing a little more in this line along the bottom. It's showing a sort of X-ray of the slot in the middle as a green indicator. And then there's a red and also a blue on the very end. And what that's doing is when you see red showing up here, that means it's measuring this naturalness and spacing stuff. But when it's doing that, if it's getting a bad result, and it considers a bad result to be not enough different spacings in this cloud of things, and it's reading the quiet beginning parts as well as all in the middle, and then the quiet ending parts again. So I'm able to measure whether that is producing a good result. Similarly to this H bloom space sustain, what that is measuring is simply how many times an echo return stacks on top of other echo returns at the same total delay. Because if it does that, my assumption is it's probably going to sound more like nasty comb filtery echo with a bunch of regeneration, and less like a washy blurry delay sound, a washy blurry reverb sound. And we have this already looking denser and more full of activity than the 4x4 or the 3x3, which has very few delay returns. If you did the 3x3, it would kind of end up going tick, 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 whereas this one goes whoosh. Hope you enjoy my verbalization of what reverbs sound like. And what this is going to do is continue to run and weight these scores so that this one, the letters here are how much this thing that adds together and produces a final result, contributing to the total score here, how much does that affect the result? Because we're shooting for the lowest possible score, meaning the least amount that these green dots stack up on top of each other, the least amount that the naturalness and spacing area has sudden changes in it rather than a continuous spread of delay times. And then the darkness and depth thing, there is a slight blue tinge to this stuff. You're not really seeing it very much, or the cyan tinge in it. And it's basically trying to measure brightness. It's trying to measure how much slew is in the resulting delay. So if you turn this one up, what you wind up doing is suppressing more of the high frequencies. When you turn the middle one up, you wind up suppressing things that count as unnatural and only allowing it if there's a nice even spread in. And we can even update stuff like this beginning or this end piece. It's set up so that if you do the one in the front, you're changing the balance of things in the front of the delay, and you do the one in the back, you're changing the balance of things at the back of the delay. Like if this green setting was set to be, say, A to Z, and we can set Z right there, we're now applying a different evaluation of it. And what we're doing is allowing stuff late in the decay tail to have more output. Whereas if we set this to A, we're going to immediately start seeing new things happen because it is running, but it's also trying to find a, and I say immediately, apparently the value of immediately isn't what it used to be. It's trying to come up with a new measurement that is, hang on, I bet I can force it in. There we go. See, the end of the decay tail had more to do with it than I thought. If I tell it, evaluate this green stuff to be less important in the beginning or throughout the entire delay tail, then it's going to start generating lower scores, and this stuff in the end has more of a significance. And that can continue onwards to the point where I'm telling it to go A to D. It doesn't care about the green section nearly as much as it did. And so now we are seeing the other stuff taking up more space. And we can go even farther. And now we're seeing the darkness and depth stuff taking more of a role. So I can make the red area become less by bumping that down as well. And what this is doing as I do it, assuming it hits upon, yep, it should be hitting upon another one, is we're weighting how it is evaluating many different criteria to determine what's going to be the best delay, the best reverb. This is before I even listen to it. And what we get on the output is what we see here. It says const int delay A equals 11, 349. You'll find that in my reverb header files, like chamber.h is going to have something that looks like the 4x4 version. It says short to start. If you look into the H file for, say, Guitar Hall will have a line of code that looks like this. And you can select this area, or indeed be clicked in here and select all. If you paste that in where the similar line of code exists in kGuitar Hall, you will get this replacement reverb algorithm. Assuming you can compile kGuitar Hall or whatever else it is, and that's something I probably can't help you with. I struggle with that stuff myself. But if you're able to run this, you can start swapping out the guts of the reverb with like tiny little ones. Or for instance, here is running it as, ideally what I should be doing is relaunching it for new numbers, especially this number here, because it wants to run on a different value. But you get to do stuff like this. We'll go back to the original setting. And instead of 200, what's it look like if it's 2000? Again, you can punch this in to kGuitar Hall or any of the kcathedrals because they're 5x5 matrices. And now we've got a much larger hall, and it's going to run and try to come up with the best possible reverb using these criteria, and also using other things like back when I did the K plates, like K plate 140 and K plate 240, I didn't have some of this stuff going on, like the naturalness and spacing and darkest and depth. I didn't have a thing that could iterate through all of these. See, it's already done 10,000, no, 12,000 as I speak of examples that it has tried to find the best one under these conditions. Back when I was doing those ones, I was able to do the thing in this G channel where I could tell it to favor stuff where all the delay was up front and was happening sooner, or all the delay was happening later. Running stuff where all the delay was happening sooner, like in a plate, you would have the beginning part be like A, but the end part would be like Z. And that would mean it would be perfectly happy to have a lot of these echoes showing up early on, but then it would increasingly frown on having the echoes hitting late in the reverb tail. And that's how we did that stuff. That's how 140 and 240 have a plate-like tonality, it's just combinations of these things. And running a program like this, often overnight, I've made it run much faster than it used to. It used to run like about 10 trials per second, and it took forever to get anything. I ended up speeding it up a great deal. That's the version that you're going to get to play with. But note that there's this button over here that we've not seen yet. And what could that possibly be? Well, this is what I don't have a working reverb out there yet, but I'm eager to try it out. 200 seats, same settings as everything. Remember how when we had like 4x4, this is as many reverb spots as we got. And then we do 5x5. And this is as many reverb spots as we've got. For only about 8 more delay lines. Well, what do you get when you go from 25 delay lines in a matrix to 36 delay lines in a matrix, which I've not put out a reverb like this? You get this? And that looks like a pretty solid thing. Remember this bit in the bottom, it's like a microscope. So you're getting a little close up into what the middle of the verb looks like. And that's a very smooth, continuous sound. You heard it in the beginning of this video because I played examples of each of the matrices, including a trial version of the 6x6 that I did. But then what do you get when you say run a much larger one? For instance, that was a 200 seat, but what if we do that 2000 seat? It'll be a little bit more high resolution. And you'll notice that we still get this kind of cloud of reverb with a very smooth, even quality to it. And that's what a 6x6 reverb matrix will do for you. And if you're doing the 6x6 matrix, it looks kind of like the 5x5, but if we scroll down, you'll see that I had to add a whole more banks beyond A to Z. So it goes A to ZK, and I had to code everything over again in order to get the 6x6 to work. But that's how we get there. And again, if I lower these, I will start to get different kinds of sounds, because lowering the settings is likely to fire off a new best score. Making the settings become lower means it's less critical as to what it's comparing against. So everything it generates from here on in is going to be around this score and is shooting for its lowest possible score. What goes on with these numbers, below where it says 1699 seat hall, is the one on the top is the total number of trials it's done. That automatically bails out at 16 million because I found if it went beyond 16 million, the program crashed. And then I couldn't copy areas in the middle of it anymore. Whereas this one on the bottom is the number of trials it's done on the current best that it's gotten to without coming up with a better one, according to these evaluations. And that one bails out at 1 million, because then when I run stuff overnight, I'll typically end up with a bunch of examples of the program. You can run multiple copies of it, by the way. I'll typically get a bunch of those, and they will all have topped out at 1 million, and they will each sound a little bit different. And there you have it. Oh, by the way, if you wanted to copy it, what you do in macOS, and I can't tell you what to do for alternate platforms because you have to be able to build the Godot Engine thing for your own platform. But on the Mac, it's very easy. Option drag gives you 2 instances. And if I run 2 instances, they're kind of mono-threaded. And we can run those separately. And there you have it. This is the tool I've been using all this time in order to make the reverbs that I make. And I'm still using it. And I'm still making more reverbs. I just decided that it was high time I let other people in on this code. And this program is now a Godot program that's MIT licensed, and you can simply use it. Or start with it, run with it doing your own thing if you want. It's fine. You can generate your own reverbs and include those into your own commercially developed householder matrix using reverbs and things of your own, because this is a program that simply generates data, and the data is not necessarily open source. You can use it to generate private stuff if you want to come up with a magic special commercial reverb algorithm that nobody has. Well, this will probably do it. It's a question of whether you're able to get to a sound that you like best using it. And you can make your own variations of the program, as I will be doing. Because currently what it's doing is it's generating a single output, and it is constantly trying to do a completely random new reverb matrix to compare against. So it'll go to around 16 million over the course of, 8 hours, if your machine is fast enough. It'll do 16 million random reverb attempts and pick the best one from that, which is how I've gotten to the sounds that I'm using. But that's not a genetic algorithm yet. That's a fitness function. What you would do to get a genetic algorithm would be generate your 16 million random examples, save them, run it, and then pick the best performing ones and crossbreed them by, for instance, taking the numbers go from like 1 to 36. There's 36 little bins that I store those values in. So what you could do is go 1 to 6 from one of the high performers, and then 5 to 36 from another of the high performers. Then you've got a hybrid. That's the genetic algorithm. You're treating the sequence of numbers that it produces as a genome. And this is something I've not started to do, but that's one way of doing it. Another way of doing it is probably what I'm going to try, which will be keeping store of either one or multiple high scorers, and then randomly, instead of assigning a purely random number, picking from one of the high scorers in any given bin and using that. That will cause particular, like if there's a hotspot where, for instance, at the corner of the matrix, it wants to be a prime number and favors low numbers like 7 or 11, which is something I've seen happen often enough that I set it up that way on purpose. If that's really so effective, it'll show up in all of the successful populations, and then it will be more common to use in subsequent generations, and that's how the genetic algorithm works. So this is a lot. And it's particularly, there's a sting in it, given that, firstly, you have to be able to run the program that does this, like the program that goes bing and draws the little picture. Having done that, you can't necessarily use the data this produces. This is just what I'm literally doing to make this stuff. So I'm giving you the tools that I do to make what I make. But that doesn't mean that you can necessarily plug this in. If you can make something compile off of my already open source reverb applications, then you can use this to start randomly and wildly trying different things. It won't care what size it is. You can go from a tiny size to a huge size. It'll be fine, or vice versa. But you do have to firstly be able to compile the Godot program, and then be able to compile one of the plugins, and then use that. So fair to say that's kind of advanced, for which I apologize. I can only say, like, well, I had to do it, so now so do you. If anybody wants to use my stuff to program a reverb where they can just read a text file with this in it and make it more user-friendly, I would certainly encourage you doing that. That would be a great additional plugin, a variation on the stuff that I do. I'd love to see it. It's a little bit beyond my pay grade to make that happen myself. But I'll tell you, if you can make the Godot engine work, I'm giving you an additional thing to play with. This is called Balls Up, and it's a video game. And using this video game is done by typing letters on the keyboard and the arrow keys to move these guys around. And if you succeed in making them go up, because that's the name of the game, you get a new level. These backgrounds are watercolors that I did. And then if you get fast enough off the top, you type for instance, here's C, here's B. If that bouncy thing sits still for long enough, and you can hear it's making sounds happen. If it sits still for too long, it shrinks away out of existence, at which point you have lost the game. So, and then if you go up the top of the screen, you get a backbeat. And the rules are still the same. Make all of these bots go off the top of the screen. And if you're hearing the backbeat, you can hit the space bar. And there is now a second bouncy ball in here that you can hear both of them playing sounds. And then one of them is shrinking out of existence. And the other one is still going. And this is the video game Balls Up. I'm not sure what the highest score has been made by this. It's better than the previous video game that I made, Counterpart, because you could conceivably stream this. And it plays music and does its thing. And then when the final timing ball, is what I call them in the code, slows down, you can no longer control it and you have lost. Although I think if your lettered balls are still moving and will go off the top of the screen, you get to pull victory from the bits of defeat and continue going. But if you can compile that in the Godot engine, you can play it. So maybe IntoTheMatrix is a weird, complicated reverb tool which is not easy to put into operation, and granted, it and all the evolution that it's been doing, even as I move it towards a genetic algorithm thing which literally does evolution, even if that is not very accessible, firstly, if you can use the Godot engine, you can play with it, even if you can't hear what it does. If I can come up with a way of making it so that you can hit a button and hear the sound of what the latest reverb algorithm is like, I will do it. And then I'll update it and you'll be able to use that. But even if you're never able to hear the reverbs that it generates unless you're able to compile plugins, if you can compile it, you can compile Balls Up or run it in the Godot engine, at which point you can play the video game. And hopefully that'll take some of the sting out of me being so busy working on this reverb stuff that I didn't have a plugin this week. I know that is not usual, but I'm giving you two things in the Godot engine. One of them's a video game, and one of them is the tool that I actually use for making all these reverbs. And that's now yours. So if you make reverbs too, you're off and running. Go ahead and take it any direction that you like. And I will do likewise, and we'll see where we get with it. On that note, I'll talk to you later. Bye-bye.